So we ended up with looking at a CSL example, so an example of a contract specification. The language is very simple, as you saw, and it's intended to be compositional. So let's look at what that means. So this is the complete inhabitation semantics. So the first semantics, I'll show you 3 of them. First one says it's a relation between the contract specification and a particular sequence of events. And it specifies the inhabitation, which means like which events are contained in, so satisfy which contracts. So if you look at the rules here at the bottom, actually, maybe we'll look at this one first. So this one here, for example, on the right, it says, so ignore the delta up there, and the delta prime is, as I mentioned before, this is a dependent relation. So the containment, or the satisfaction of S belonging to C2 depends on bindings of variables to concrete values, which are stored in delta prime. We'll see later how they're used. The uppercase delta, the upper delta there you can ignore here. That's a global environment, doesn't change. So this one says, well, for a string or for a sequence of events to be contained in C1 plus C2, it is sufficient to show that it's in C1. And the other rule on the left, of course, is the dual one. So this one basically says this is just containment in the union. So the interpretation you can see already is the union of the sequences that satisfy the corresponding contract C1 and C2. For the concurrent or parallel composition, we always call it AND, but which might be a little bit confusing because it says that for a sequence S to belong to C1, C2, C parallel C2, means that it has to be able to, you have to be able to decompose it into an interleaving of S1 and S2. This is what that means. And then show that for S1 has to be satisfying C1 and S2 has to be satisfying C2. The whole point of actually what I'm showing is like there shouldn't be any surprises. So the interesting part then is, this one is not surprising either. The concatenation of 2 strings belong to concatenation of 2 contracts if and only if S1. So there's a way of splitting S into 2 parts, one S1 and S2, each one satisfying their respective contracts. And the thing that makes it special in the sense that we make updates to the environment and have a satisfaction relation that requires an environment is that if we have a prefix expression like this one, so a transfer, that one is matched by a sequence of events, the first one being a specific event, namely it's a term of the form transmit, it has to be that one, and then it has arguments V. These arguments are 4 arguments in this case. They match the contract capital X bar P dot C if we can do the following, namely the event that's coming in is of the form transmit, so we've written this down in the conclusion. And furthermore, it's the case that if we've taken the binding that we get from the transmit X being matched by the concrete transmit V, so that's the binding here, that says, now we're taking all the bound variables in transmit X and we're binding them to the concrete values. That way we extend our environment, so we have more bindings. Then we ask, okay, there's a predicate mentioned here, P, which can have all the free variables occurring in the environment, so including the ones from the X, so it's evaluated in the environment delta double prime. So remember also there could be already some variables that have been bound in previous transmits. They will be in the delta here. This should have been delta prime, I guess. No, it is. So that's true, yes. It's a delta double prime. So the delta double prime we're using, is the predicate satisfied or not? If it's satisfied, if it's true, sorry, I should say, if it's true, then, you know, we need that in order for the transmit V to be a match. Otherwise, you know, the rule doesn't trigger, so the transmit V does not apply. And that's basically it. So the rest shouldn't be surprising. Just, you know, we have recursive functions, and they just unfolded and then checked. Okay? Yes?
So the S's, that's just what are the S's again?
The S's are sequences of events. So they're elements of...
So an event comes in which does not help any contract forward. So
Yes.
it's like a junk event where
Yes.
the rule drops it.
So right now, if you think about the semantics is just a classifier. It says, it doesn't say that something's coming in or not coming in or how to process an event as it's coming in. This one is just classifying any given sequence of events into either being a satisfactory sequence of events for a given contract or not, okay?
So now, if you get one junk event, then in another ways, okay sequence, that would just mean that it does not hold for this semantics, but you could relax it.
Maybe I'm misunderstanding your question, but if you get a junk event in the sense that something that doesn't match the prefix, then this semantics just says that any sequence that starts with this element, we can conclude from the semantics of this thing, you know, that no sequence will ever, you know, match it, yes. So we'll operationalize that in a second when we talk about, you know, how we do process sequences of events one element at a time, or one event at a time, okay? So this is, think of this like, that's the canonical semantics for inhabitation, you know, which sequences of events are denoted by a given contract. Okay, so denotational semantics now is one that says, well, let's define actually the sets of sequences of events by induction on the syntactic structure of contract specifications, okay? I want to talk, so not surprisingly, you'll find, because there's recursively defined contracts in there, we'll find there's a least fixed point operator, so the domain here is just subset containment for the power set in the domain, which the domain is the power set over event sequences, okay? So there's no, it's a first order language, there's no, we don't need to lift any domains. It's a natural, it has the monoticity we require, you know, it's even continuous in that sense. And here we'll see that it's basically satisfaction relation reworked to make sure that we're gathering up the set of all sequences that satisfy a given contract, okay? So here you can explicitly see then the plus is interpreted, so the plus combinator is interpreted denotationally as just a set union, okay? The concurrent or the parallel operator is interpreted as the interleavings. That's the interleavings here of the two sequences that we have. And the concatenation operator is interpreted as the concatenation on the languages, you know, on the sets of sequences that are denoted by C1 and C2. And here this is basically saying just this is the set of, you know, transmit starting event sequences with an S at the end that just codifies what we've seen in the other one. So I just want to point out here is that if you look at this, then you will squint, if you squint a little bit and you take out those parts that are really important for contracts and resource management, namely all the arguments. So imagine now the transmit will just ignore, you know, that transmit has any arguments, okay? So we'll just think of it propositionally. Maybe there's some additional events in there, you know, types like transmit and inform and so on. You can think of that way we get a finite alphabet, right? So right now I only have a finite alphabet consisting of one, it's unary, because we only have transmit as a primitive event. Now imagine actually you removed all these arguments, I mean the arguments from the functions, and the arguments from transmit, and kept the rest. Then you will see this looks very much like something you've probably seen before, namely if you take out the parallel concatenation and you just keep plus and the semicolon, and you have the recursion in there, but let's imagine now we make it just tail recursive, okay? So, you know, the f's are only called at the end of expressions. Then what do we get? Anybody would recommend or, you know, recognize this? Yeah, regular algebra? Sorry, yes. Yeah. Kleene algebra, exactly. So we get basically, well, we get the syntax of Kleene algebra, and the semantics that I've shown here would be a language semantics which is complete, which is the you know, the regular languages for this. And you know, and then we have this concurrent, this par operator, and then you know, you could say like, what properties does it have, and it satisfies the properties of concurrent Kleene algebra. So conversely to us, that meant when we look at this one, this is actually an open area, you might say. It's like right now we have an interpretation of contracts as sets of sequences, right? So it's a sequence language. But one would then be, also for practical reasons, you see that having a sequence of events when you have this concurrent par operator, this is kind of like an unnecessary interleaving semantics. So then we might say like maybe we can get away with a POM set semantics, which I mentioned before. Okay, so and generalizing that semantics then to this richer domain where we don't only have propositional, you know, transmit as an atomic event without any arguments, but we really have to reason about the states that are attached to it, namely the arguments to transmit. That's that would be interesting to have a closer look at some point. I got to go forward. Now, why are we doing this? Well, the title. Sorry about that. So, Theorem 1 says, not surprisingly, is that this, you know, the denotational semantics captures the satisfaction relation. So the first thing that means is that before we could reason inductively on containment statements. Now we can also reason inductively on the syntax of contracts, because they give us, if we get something right about one, then you know, it's correct about the satisfaction. So we get a different reasoning principle from this equivalence or inductive reasoning principle. Now, from denotational semantics to operational semantics. So we're actually interested in finding out if I have a contract and I get the events in one at a time. So the satisfaction relation basically says I have a contract and I get in a whole sequence of events, then I can start thinking out whether it belongs to that contract or not. But now we want to do the following. We want to do this one step at a time, one element at a time. So the analogy is basically the satisfaction relation is basically the grammatical view, okay, of sequences of events. So when you write a grammar, you think semantically, and you usually write the semantics down as saying, oh, it's you know, whatever can be derived from the start symbol. So it gives me, you know, it can expand the start symbol into a whole sequence, okay? And then what we do in language theory is like, oh, that's great. This is like, you know, I would call it the side view, right? So think of it as like there's a sequence of events here, and I'm stepping over here. I'm looking at it from the side. Okay. Yeah, the left part fits with the first contract, and the final part looks, you know, maybe I can split it differently here, okay? So it fits like this, and it fits like that, okay? So I can look at it from side view. But in practice, very often, we're in the position we can't look at these things from the side, like they're stored in RAM, and somebody has put them there before we start thinking. We actually in the kind of streaming position, so we're over here. So these events are coming at us, okay? So it's like, I can't do that. So they're just coming at me, you know. So what are we going to do now, right? I want to get the same result as from the side view, but I have to do this now one at a time. So basically I have to write a processor that is streaming through the events and doing something useful. So in what state am I now? In what state am I now? And so in the end, when I'm done, I get the same result as the side view. Okay, and that's basically what the operational semantics does. So it tells us how to actually, the way we did it actually, literally, it was very useful to have a denotational semantics because we were kind of like hacking around, to be honest, with operational semantics. What could these, these are useful patterns of contracts. Let's come up with this rule. And yeah, it could also be this rule, and maybe should actually favor the left one. And, so it didn't feel right ever. So until we had to step back and said, what is the domain of contracts actually? Well, let's just stipulate its classifier of event sequences, write it down in a denotational fashion, and then derive the operational semantics from it. So not surprising, the main theorem will be, well, there's an operational semantic that operates on events one at a time, and it is complete and sounding complete for the denotational semantics. So the key thing is like, and this is definitely not readable. The key thing is these semantic equalities, basically figuring out if I have a contract. So the whole idea is the following, is like I have a contract. Remember, we already defined the residual, but it was semantic. So every contract specification denotes a contract, which is a set of event sequences. And it's well defined that if I get an event, then there is actually a set of event sequences that's denoted here. So here, can I represent it by a syntactic construct here, by a contract specification? And the answer is yes, okay? So we'll figure it out now, how to represent it. And the key thing is like, if we have a contract that is success and somebody says, oh, please match it against E, then we'll say, oh, at that point, it's failure, okay? Then, if you're already in a failure state, then, somebody insists on you matching E, definitely doesn't, it's not an expected first event, failure. Then if we have E of FA, of course, that's just the expansion. So we look in the body of this one. And if we have a transmit event, then we'll do what is not surprising. Namely, we'll say that, oh, okay, this matches only against the transmit event, in the contract. If we had other ones, it wouldn't match. And we bind the X to the V, and we have a continuation. So the residual contract is just C with the V's bound to the free variables X. And the part that is actually not surprising to you, I guess, but is actually shocking to people who are dealing with bookkeeping or with accounting, is that if it looks like you have a choice, like, you can satisfy the contract by either doing C1 or C2, and somebody says, like, here's an event, somebody's made a payment, okay? So it, you could apply it to this contract or that contract, C1 or C2, because, the user can satisfy either one of them. Then standard practice is like, I need to find out now. Is it C1 or is it C2? What if E actually matches both C1 and C2? What do you do then? Well, you would say, well, let's delay it, and that's what we do here. But, in practice, very often you see that people insist on getting something in, saying it's this or that. So I'll just, make a choice now. And in this case, you could actually hit it wrong. But, the correct, this is an equality here. So these two contracts denote the same set of events, is of course that, you apply the residuation to both subcontracts. Yes?
I think you're actually getting at this distinction that you're making, like when is the choice made between two alternative contracts. I think you're actually getting at something very fundamental here, in that there's this classic distinction between language equivalents and bi-assimilation equivalents, which is well known in process algebra. So it depends on the level of detail you want to look at, right?
Yes. So just to elaborate on this one, that's exactly the key point here, is that we have a language semantics, like sets of sequences of events. So decisions made, remember I just said like, oh, there could be a decision, to go either choose the left one or the right one. They're not events, okay, in the semantics, okay. If they're not events in the semantics, we'll naturally end up with having choices not be observable, okay. And we'll end up with, language semantics. If we made the choices also observable and saying like, oh, that's a different event sequence because you made a choice here and not later on, then we'd end up with more like a CTL-oriented language, with a concurrency calculus-oriented language with bi-simulation. And you can do both actually. So, but here we've sort of made a choice to not make the choices observable, visible, okay? So in other words, we call it deferred matching because it means like there is no choice made. Okay? Nobody makes a choice. There's no internal, no external choice. It just means you're in this kind of entangled state, okay? So the plus you can think of is like, you know, in the end it's going to be only one of those two. But we don't know which one. That if it turns out that once the next event comes in, the second one doesn't match anymore, then it becomes failure, and you know something plus failure is just the same thing, it's just something. Then it's like, oh, it's disappeared, which means like, oh, we've sort of like, you know, it's fallen out to be the first choice. So it's just non-determinism in the standard sense. Yes.
If you have two identical contracts.
Yes. Yes. No, because you will get from the reduction rule that they will both actually reduce all the way down to, if let's assume they get accepted, to success plus success. Okay. And then you could say there's still this kind of nasty kind of feeling you should have. It's like, you know, shouldn't I know whether at some point the left or the right was taken? In this case, we have a semantics that says no, because the only thing you're interested in is satisfaction. Hey, you are lucky. Whether you actually have two different ways of succeeding or one doesn't make a difference here. But there are semantics where you would say like, oh, I want to keep track of how many times or, you know, which one I'm choosing. And then we get into the situation where we have explicit events about choices made. And they give us actually a much more refined semantics and naturally lead to a you know, branching time logic or to a you know, label transition system semantics and equivalence. And but we haven't, you know, investigated actually the theory of actually the you know, label transition system semantics. So, but this one falls out of the domain. You know, if you've chosen first, you know, we want to interpret the contracts as a sequence of events and a set of those, that's what we get. And then, you know, quite clearly you get the same one with the parallel concatenation. It just means that, well, you get two choices. Either it matches on the left or on the right. So the plus really tells us, well, you know, that it's a deferred choice or it's not really a choice. It's either one or the right. And maybe some of them, one of them actually will die away, reduced to failure, as I mentioned before, and then only one of them is left. Either is nullable, I won't mention that. So this theorem basically says that now with that reduction relation, the reduction relation is sounding complete for the denotational semantics and so for the satisfaction relation. So it reduces to something that contains success, that's the nullability here, if and only if that sequence of events satisfies the contract. All right. This is going well today, for once, time-wise. So let's have a little discussion. So why have three different semantics that turn out to be equivalent? Okay. Here's what I would argue. Some of those is kind of like soft arguments, but I think important ones. So we get, from that one, we get three different inductive reasoning principles, okay? So from the, we get induction on proof of containment. So you got to think of it as like induction on the legal parse trees of a sequence of events. And the parse trees here mean the containment proof that it satisfies a contract. Then we also have induction on the abstract syntax of contracts. So, which is the denotational semantics. So we could say like, I want to prove something about the set of sequences that is denoted here by all of them having a certain property. And you can do this by induction. So this should be leading up to something like, you know, type systems or abstract interpretation that is classical denotational abstract interpretation in the sense that it's compositional on the syntax. And the last one is like just simple, you know, induction on the length of event sequences. Because that means like now we have a way of reasoning about what is the state of a contract after 1, 2, 3, 4, 5, and so on events. And that's the operational semantics. Then the semantics-driven language design, I think, was very important to us. So we started actually after a while by thinking, what is it really that a contract should denote? And that really means is like, what should I be able to observe about it, and what should I not be able to observe about it? That's maybe the most important part. And then we decided that we ended up with the domain of the set of sequences, okay? And it had exactly the consequence here. We basically ended up with a language model. But that also gave us then a systematic way of deriving containment and denotational semantics, and from that one, a correct operational semantics. And then also the correct operational semantics is like a benchmark for actually engineering it. So in practice, actually, that's not implemented. So the current implementation in Deon Digital CSL is sound for that, but it's not complete. So it's basically saying, I'm a manager of these things, and this is the truth that I should be implementing the model, but I can tell you that I'm actually only accepting a subset of those, because I can tell you what state I am, and I'm making certain choices that are more limiting than what this semantics says. So I'm making commitments, basically. It's just like the analogous thing would be like, this semantics is like Prolog, the full formal Prolog, but you know, the implementation of one of the interpreters we have, or the monitors, is that there's some cuts in there, okay? That's the same problem with a cut, which means that certain alternatives, when I mention the pluses, they just get cut off at some point. Just like you usually do in parsing, so we have finite look at it. So there is a systematic derivation of the automata view, which is very important. So you could say like, we took the and then derived from it, you know, the important key thing is like the automata view is like one at a time, processing one event at a time. And it's a baseline for engineering aspects of how to represent contracts, the internal state. And an important part of this is actually that the internal state, so if we start with a contract, a thing called a contract, specification, the internal state is always just a contract, nothing additional, okay? So internal state is always representable as a contract itself, which has actually interesting consequences. So one of the things we want to do with contracts is analyze them. I'll mention a couple of those things later on. Just, is this fair? Or, what are the next events and all these things? What's the price to one of the parties according to stochastic, valuation of various parts? The key thing is like once you can practice and actually apply the analysis to an original contract as you enter it. Should I enter into this contract or not? Let's analyze it, okay? But then once you've entered it, you have a running contract. You can use the same analysis at any given point in time and apply it to a residual contract. So you get automatically, you can't avoid almost being able to analyze running contracts if you can analyze initial contracts. So let's take a little summary here. So CSL is with denotational semantics, gives the compositional view, satisfying relation, and the CSL with monitoring semantics. We've already seen that. That lets us take the monitoring semantics, which was idealized because it operated on the semantic domain. Now we can lift it out into the syntactic domain because we have a syntactic representation of every contract in CSL, and we can represent the derivative or the residual of a contract after an event by a contract specification again. Great. So let's look at some more. So as I promised, we'll make this a little bit more open to some, and some. This is ongoing work, and some of it is been done. But I think there's a lot more to be done in the area of contract analysis. Also because that's the promise of it is that what you want to do is you want to verify properties about contracts, and you want to analyze them. So I'll just propose some introductory, some basic terminology and give examples of analyses that are important in practice that seem viable here to perform, definitely sound enough, but also concrete enough and precise enough to be valuable in practice. So this is actually the standard recall thing. The bottom thing is just what we've added here today. Okay, so we have contracts and contract specification. So a very important part, and I can tell you in practice actually, what people are struggling with is like not the advanced parts of, quantitative analysis of contracts and for financial, volatility or pricing or risk, but actually just managing them, like in what state is my contract? Because you usually have 1,000 of them, or maybe 10,000 of them. So you have a whole portfolio of those, and you have to know in what state am I in. So the life cycle management, keeping track of what has happened and in what state am I now in. You might say that's surprising. Well, the whole idea of this one is that it should be not surprising anymore, because now we have a representation. We have an explicit representation of the internal state. So if somebody said, oh, look at this operational semantics, this interpreter that does it, and you look at the data structure in there as a data type, and if you write in GADTs with Haskell, then you get a lot of typing also for free. And you say like, okay, what's the state of this contract? You just look at it and say, look at the data structure and say, oh, okay, pull it out. It's it's a tree. So let's look at this one. It looks like it's a prefix thing, and then you have to actually do a choice between that, and there's a par. That's the contract. Isn't there something missing? Like the time requirements. Aren't they in some other code base or in a database? No, they're not. It's a complete description of the contract. In particular, you can take it and say, you take it now, okay? You manage it now. I'm tired of it, okay? So try to do that in the real world, okay? Where you have usually fixed contracts and there's a stack of software that says, I'm managing these kinds of contract, but there's never a specification, explicit specification of the contract. There's only code that does something with it. It doesn't do anything with it, but it says, oh, I'm pricing this kind of contract, like, I don't know, a swaption, okay? So with these parameters. But there's no representation of the swaption itself that says, oh, okay, I have to do something repeatedly, or I have, now I can, I have an option to get a swap and whatever. And what does that actually mean? It's not written down. It's in people's head when they write the code for analyzing it, or when writing specific code for that kind of contract. It says like, check that these things happen, and you get the payments of interest and all these things. Sounds banal, but it's a very important part of, and it's a key aspect of having explicit representations of contracts, independent of how they're managed. So today, let's look at a little bit of contract analysis and some exercises and open problems. I mean, that's not a lot of it. So let's first try to establish a basic terminology. So a contract property is a predicate. So in the sense, again, of a Boolean function on contract specifications. So it's a predicate of syntax, okay? So you give it a syntax, and the syntax says yes or no. So there might be different properties, and of course we're interested in different kinds of properties. It's an extensional property if it has the property that if two different contracts denote the same set of event sequences, then the property holds for both of them or none of them, okay? So in other words, it's what we usually call an extensional or semantic property, okay? You could also ask questions like, how long is this contract specification? I mean, how many bytes? I mean, how many characters does it have? That's clearly not an extensional contract specification. But we're most interested, of course, in the extensional ones. A universal one, it's not so important, but it just means that very often we're interested in a safety property, a property that says, like, we want something to be case for all sequences that are denoted by our contract. You could also ask, well, does there exist a sequence at all? For reaching, that's a reachability state, property. But universal is very often what we're interested in. We won't use it that much here, but that's presently what we're mostly interested in. So contract verification. Yes.
Can you give an example of a probability node?
Yes. How many bytes? How many characters does this contract specification have?
Okay, so
I don't know. Yeah.
they can express something about the syntax.
Yes, exactly. So yeah. So they all feel like there's something they're asking about the syntax. And especially decidable ones, necessarily. Well, yeah. There's a little bit of the predicate language I mentioned before. Technically, it's the case the predicate language didn't, the language of writing predicates. So you could think of that one, that's a sub-language. So the contract language is parameterized by the predicate language. So if you put a little bit into the predicate language that's expressive enough, the whole thing, of course, is undecidable. But it's still interesting to ask the question how expressive or hard is to decide questions about contract equality or equivalence in that sense. If you have a P thing. But you're right. It's mostly, if you can decide things, then it's usually you asking a syntactic question that's not extensional.
Especially after the addition of semantic theorem.
Yes. Sorry?
If your property states something about semantics.
Yes, that's what I mean. Yes. Yes. So mostly, we're usually mostly interested in about the semantics. In terms of like when I'm asking a question about the contract specification, most likely I'm not interested in, I don't know whether I use the word, how many uppercase letters I have in the contract and not, but I'm interested in asking about the question about what it denotes. And that's exactly what extensionality expresses. So it's a semantic properties one that is about it's about the semantics of a contract, independent of how it's rendered. So just terminology. So a little bit fluffy, if I might say, but it's actually the way I think it's good to think of as a contract verification means like given C and the specification of a predicate, a property, we're interested in decide whether P of C holds. Okay. So I have a contract. I want to make sure it has the property P. Is it the case or not? And then you go off and you say, yes. Ideally, we like to have usually a little bit more. Namely, if it holds, we might ask, maybe there is a proof in the sense of expressed in some kind of logic that documents, that's sound for this, of course, that documents that provides proof evidence that P of C holds. And we might actually also be interested in, if it doesn't hold, in getting a proof or some kind of evidence that, why it doesn't hold. So here's a proof why it doesn't hold, okay? But, very often you might just get something that says, I don't know, or I can't give you a proof. Because the I don't know has to do with the fact that, it's sound but might not be complete. In the sense that, sometimes you get a response that says, I can't tell you that's definitely the case. I cannot tell you either that it's definitely not the case. So it's somewhere, I don't know, okay. And contract analysis is basically verification where we're looking for a good argument to such a predicate. So think of P now as a two-argument predicate, and it says given C and such a P, compute a good E. Compute a good abstract value E that, for C, such that, the property we're interested in, namely P of E of C, that should be an uppercase C, holds, okay? So it's just a way of saying, like, please give me an abstract result. And why is that a good abstract result? Oh, it's because it's related to my semantics, okay?
Is that like
Sorry? No, I shouldn't have used E here. No, it's just an abstract value. So for example, let's look at this here. First events, let's look at that as an abstract interpretation or as an analysis, okay? So this is the E here, and I've used the E for something else before, namely events. Sorry about that. So this is a different E, okay? But let's look at an example here. So the definition of first events, which is curious, and we've actually used it, called it next events, but it means like the next set of events that are possible. So, but in language terms, usually you learn that that's the first set, okay, the first events. So the first events is defined to be all those, the set of events, and yeah. This is two different E's. This is really bad, okay? Yeah. If you stare at it very hard, you can see it's clearly no, it's actually the same E. So, yeah. So the second E here means just event star. Okay, so this means like this set of sequence of events. And the E here is the one I'm looking for. Okay. No, sorry. Now in this case, I'm wrong. So this is actually the same E. Okay. So if you look at it, actually it is the same E. Yeah. So so what we're looking for, let's look at the formula again. It says we'll look for all the events that can be the first ones of a satisfying sequence. Okay? That's all it says. And it's a lowercase c, so that means that's the denotation, or that's this set of sequences. So the analysis problem we have is, given the contract specification, capital C, compute a useful representation of some set different E, okay, such that the first set is contained in it. So it should be sound, okay, so we don't overlook an event, but it shouldn't be much bigger than necessary, okay, that's what I mean by good. So it should contain all the firsts, and ideally should be exactly the firsts, but it's sound if it contains those, okay. So how would you do this for the CSL contract specification? So look at the syntax. So somebody hands you an element from this grammar, a contract specification that says, yeah, so can you compute a representation of the set of possible first events? That's a very useful tool, by the way. It's like if somebody is sitting there and saying, oh, what should I do next, or what should happen next? It would be nice to get a list. It's like, these are the things that should happen next, okay? So, yeah, just, how would you go about it? Yes?
You could sort of recurse
yeah.
down the syntax until you get to one of the base terms, and then turn that set of that union.
Yes, exactly. So you could say that's exactly it. So basically, if we didn't have the dependency from transmit and all these things, but you could say, well, the dependency of the transmit doesn't really make a difference. It only means that the dependencies catch actually after the first event. So we're lucky in the case that they make no difference. So we don't even have to keep track of the dependency, because the question is only about the first event. So we'll just recurse recursively over the syntax tree and collect up the first events, okay? Now the first events, remember these are specifications, so they could be transmit A1, A2, RT, such that P. So we'll collect up in reality these expressions, and they're expressions, okay? So we can, but at least we can say, like, this is the possible set of next events. Now, if you had written this in a general purpose language, where actually the contract specification is not given as a specification, but as a program that accepts an event and does something for it, and then prints out something, logs something, would that be more pleasant or less pleasant? Figuring out, coming up with an analysis that says, oh, now I need to analyze and figure out what is the possible first events. I would argue, yeah, great. So I would argue sort, because then in the situation, now we have to interpret all of a sudden general purpose programming language statements, if and all and while, and there could be arithmetic constraints that have something to do with the manager actually keeping track of something. We have to analyze all of those. So because we're embedding basically, intuitively, if you think about it this way, we have a DSL, it's a small language, it lives in a very small space. Once we have a monitoring semantics written in a general purpose language, then we're embedding actually the semantics of the DSL inside of a huge programming language, a GP, a general purpose programming language. Now we have to analyze general purpose programs to get to the same result. And as I said before, this enormous expressiveness is usually very hard to overcome. It's usually a lifetime job working in that area. So of analyzing general purpose programming languages. Okay, so if you go back here. Now, here's one thing we're actively working on right now. You're absolutely welcome to work on this one. So this is a fundamental property that I haven't really seen people analyze yet. So let's call it fairness or fair consideration. And it's a very fundamental property that you'd like to have for a contract, and it involves all the terminology, all the concepts we've had so far. Okay, so basically we've been leading up to being able to define this one in a single slide. Namely, let's assume there is a transfer effect function f given. So that's built into the notion of our semantics. Now, given a valuation function, so remember we started with this one, like let's call it price, that maps every resource type to a unit price. Okay, so that's sometimes, mark to market. Somebody says, oh, what's one iPhone 5 worth? What is this bicycle worth? What is this kind of commodity, actually 1 kilogram of it worth? How much is 1 yen trading for today in a reference currency? So think of it as saying we're mapping every resource type, 1 unit of it, to a price in dollars, okay? So the only thing we need to know then about the dollars is how many dollars. It's a real number then, or something like it. Let's call that the value of sequence of events of, so a given sequence of events is, we could say, that's the value to all the principles, all the agents in it, not just a single value. For every agent, we get a value out of this one. It is the following. It says, take the sequence, extract the transfer. There's a single transfer, we've seen that last time, that is denoted. That's the effect of that particular sequence. Now we have a single transfer. Now we can apply the single transfer. A single transfer is, so a single transfer, remember, is like for every agent we have a resource. Then we can map the prices, the price function, over the resources, and then we get a map for each agent, that maps each agent to a dollar amount. So you could say, wow, okay, given somebody gives me a price, I can then value any given event sequence. Then we'd say, okay, given that's the price, we'd say like a contract is epsilon fair for a given price function. So that's important because usually there's no, prices change, Tomorrow, something has gone up and something else has gone down. For a given price function, something we call it epsilon fair, if for all the event sequences in the contract, so for those and only those that are happy paths, and for all the agents in the world, but mostly means that for the ones that are participating in this one, it is the case that if you look at the value that we've just computed and project out what is the value under the price to that particular agent, it could be positive or negative, okay, or 0. So we'll just take the absolute value of this one and say it shouldn't be too far away from 0, okay? Because the idea is that if you have a fair trade, and I give you a house, and you give me $5, and the house is $1 million worth, that's what the price says, then under that valuation, you're up 990,000, whatever. You're up almost $1 million, and I'm down $1 million in this value function. Then we'd say, if the epsilon is only $100, then we're very far away from that, okay? Or it's $15,000, But on the other hand, if what we exchanged was not a house, but it was just, a coffee latte, which is actually under $5. So here, it's more than $5 in Denmark, so that's great. Then we'd say, okay, that's within $2. That's fair enough. Okay. So then we say that the contract specification is fair, epsilon fair under price, given price, if the contract it denotes is so, which means that for all the sequences of events that are happy paths. All right.
So like value, like it looks like in the first equation, it only has a function of s, right? But in the second equation, right, when you have the bound, you have like an argument of a.
Yes.
So is it going from like a function of one argument to a function of two arguments?
Value s. So that's the reason I wrote this down here. So it turns out even the sum, it sums out to 0, but still, it basically means that value s is an element of this vector space, which means that it's a map from agents to real values. So what this means then is value s is that map, and then we apply it to a single agent, then we get a real value. Okay? So this is actually something we're working on, and by trying to give an analysis, and you're welcome to look at this one, because I think this is not an easy problem, but it's probably we have a domain and where it's important to analyze this, and a language where it's probably feasible to come up with decent enough analyses, and maybe also with disciplines of how when you write down a contract specification. So think about like your program designer. You can give it's like if you program in ML. There's certain things that you do to avoid type errors, okay? You can always code around type errors, but there's certain ways of making sure your program is well typed. So what we hope to accomplish this one at some point is like getting some kind of reasoning principle about fairness, again, hopefully compositional, such that if you abide by the reasoning principles, then you get basically a logic of fairness that will actually guarantee that if you design a contract, you design fair contracts. But that's open, so I mentioned that now we're kind of in the world of openness. And I think nobody has worked on this one. So in some areas, people analyze these things from a game theoretic point of view. But remember, very often the assumption is the following. Something is fair, is a good game, assuming an optimal strategy by all the participants. Okay, here we're actually going way further, okay? We're saying like, people can use a bad strategy, okay? And if they do something really stupid for themselves, then we do not call it epsilon fair. Okay, because maybe somebody who composed the contract was speculating that, the counterparty is not a game theoretician and, can be duped into not, forgetting to actually make a call when, of an option when they should have done it, okay? So why is it important? Epsilon fair contract, where the price reflects market prices, guarantees that no happy path leads to a state where an agent has more or less than the others. The combined with the transactional escrow contract execution, we get actually a double protection, you could say. So this is only for the happy paths. So imagine you have something that's fair enough for all the happy paths, but what happens if we have now an unhappy path? Somebody breaches, the execution doesn't terminate. Well, if we have an escrowed execution, if it's possible in practice, it might be difficult to insist on somebody returning the bike to you. But in principle, now we have a way of guaranteeing that a happy execution does not get people to be unfairly treated that are involved in it, and an unhappy execution leads to a zero. Basically zero, it's a zero fair, right? So you're back at having exact resources you had before. And the key thing is also that this is a parametric in the sense of it depends on the price. So instead of trying to build it into so statically build it into a contract saying, oh, this is a fair exchange and this is a fair exchange, that seems rather far-fetched to try to do that, because clearly the valuation of things changes. And what is fair today might not be fair tomorrow, or the other way around. So we did not design a static type system that has, so only fair contracts can be expressed, because they clearly depend on a parameter, the extra parameter being market prices. Okay, last part, so maybe we take a break, and I'm I'm just posing one more question for those of you on the relation of linear resources as modeled by transfers and linear logic. Is there a connection or not? And that's partially, I'll give you some hints. I was all obsessed with that in the plane here on what that looks like. But maybe there's more to be found out about this. Maybe some of you already know that this has been solved. But in order to make sure you don't have to listen to my cough a lot, we'll have a break until 4:50, and then we'll have another 10, 20 minutes if that's okay with you. Okay, thanks. Linear recess, linear logic, and I'll turn off the mic. Turn on the mic. So, linear resources and linear logic. So linear logic has been called a resource logic. I imagine maybe some linear logic gone through it as a resource logic. So the fundamental idea is that when you use an assumption, actually not using it only using it up, it's gone. Something else to use it twice. Well, they're competing twice. And the transfers here, they guarantee something, namely they guarantee also linearity. So the preservation of the total amount of resources. So the question you would ask, this is open from, kind of interesting to me at least, so maybe it's shut down. Kind of interesting fragments of linear logic being known as linear maps on transfers. So interpret the sequence, the judgments of linear logic as a resource transfer, and then the implications as linear maps on those. And linear logic has no, so if that's possible, then there's certain operations in linear logic that don't sound familiar. They're not expressed here. So for example, you can't scale something k times, or a fractional number of times. So what does it even mean? So it's like, here's one linear implication, so please use it many, many times. We have a bang operator, so use it arbitrarily many times. But what if somebody said, like, yeah, I want to have use it k times? Then you say, oh, that's no problem. You just write down A linearly implies B, and it's a tensor and A implies B, and A implies B, and so you basically enumerate one for one the number of times you want to apply it. So you could say, that's good enough. You'd say, like, wouldn't it be easy to just write down, I have 264 of those applications, or these implications. Maybe just write down 264 times this one. And then you can get into a funky area by saying, like, I just want to apply it 264.33 times. So, oh, what does that mean? Okay, well, so that's basically the questions here. So just to refresh some of the rules of linear logic, and then we can maybe look at them jointly and see if we can find a connection to the model of resource transfers that we've seen, 2 days ago. No, yesterday. So the first one is so first of all, I'll intentionally provide you with a view I've heard is not popular. This is classical linear logic, where everything's on the right-hand side of the one-sided presentation of linear logic. All the statements are on the right side of the dash symbol, V dash symbol, implies symbol, the judgment symbol. Sorry? Turnstile. Thank you. Finally, yes. I haven't been in New Jersey for a while. Anyway, so the exchange one basically says the exchange rule is like the only substructural rule we have. It says that the order of our formulae don't count, but we can permute them, but we can't remove any or we can't duplicate any. Now the init rule is actually quite crazy if you think about it, right? It says that out of nowhere, there's no assumption, out of nowhere pops both any statement, any formula, and its negation. Yes?
On the right-hand side, it's read as or.
So the intuition, of course, is that that's what this is about. Is like, how should we interpret this kind of comma in different ways? So the intuitive interpretation is that it's an or of some form, okay? So then we'll say like, oh, this is quite classical, that we have a classical or here, in the sense that for any A, it's the case that either A or not A holds, okay? So that's the init rule. The cut rule says that, how do we get from, how do we make conclusions about having produced something? You know, now somebody has figured out that maybe, you know, in the sense of, you know, gamma or A holds. How can you use this, you know, as a lemma? The lemma then says that, oh, the cut rule says that, sorry about that, there's a turnstile missing. So here should be a turnstile. Then the cut rule says like, oh, if you have such a lemma, I can use it because I'm depending on A holding. So, you know, I'm saying like, oh, either A does not hold, but now somebody has told me it does hold. So I can conclude that, you know, all the other disjunctions still hold. So it's the case that gamma holds or delta, okay? Because we've eliminated the possibility of not A holding. Now the multiplicative rules, they basically say that whatever you have, that's the resource ones that say whatever you've produced, you really actually have, you can use every component of it. So if you have produced that from an A, or actually a gamma holds, and you've produced a B, or maybe a delta holds, so intuitively two different alternatives to A and B holding, you could say that, well, then it's gamma or delta holding, or actually then you know, the conjunction of A and B. So intuitively, you know, you've gotten A out of, you know, if you move them to the left-hand side, they become conjunctions and negations of that. So basically, given you know, what gamma has to offer, I have produced an A, and given what delta has to offer, I've produced a B. Then if I have both gamma and delta, I can produce both A and B. And both A and B, that's the tensor here, the tensor product, tensor unit. And then the par basically says, you know, it's like, you could say like it's, I have both a choice between, I have a full choice between A and B. So, so either A holds or B, so we just represent the comma up here as a par, we internalize it. Par unit, I won't go into those. And then there's also the additive rules, you know, that say like, you know, if you have A and B holding, then you could say like, you know, but they both are actually pulled out of gamma, then, you know, it's basically, you can get both A and B, but not both of them independently. So you, at some point you have to make a choice and choose either one of those and plus. So let's look at those rules. Maybe best thing is to look at these first. Is there any idea, you know, and I think maybe let's just look at the structural rules and the multiplicative rules. Is there a way of interpreting, relating this to this kind of notion of this kernel of a sum function over a coproduct of resources? Well, you think of it as really intuitively, okay? So we've called these things resources and, you know, and ownership maps where, you know, now we have explicit owners here, but you can think of, you know, the position where something occurs. That position owns, for example, B. Well, one way of starting, right? Any ideas? So I'll start you off with an idea. Maybe there's other ones that work, or maybe you'll find out this doesn't work. So let's look at this one. It says that, it's called the exchange rule, okay? So, okay, it looks like it's a transfer, right? So if we read such a event as a resource transfer, so let's interpret it as a resource, let's assume it's a resource transfer in the sense that, well, gamma is usually a sequence of those. So it has, you know, positions 1, 2, 3, 4, 15, right? And then we have in position 16 a B, position 17 in A, and then we have another, I don't know, 30 positions in delta, okay? Number of commas. But the key thing is like, think of those positions now as the indexes we have, as our owners, as our agents, okay? All right, that's our index set of agents is now just, you know, numbers, indexes into a sequence of what? Of resources. So let's interpret actually every formula we have as a resource, an element of that coproduct. And let's assume furthermore that we insist that the sum of all the resources is 0. So it's a transfer, okay? Yes?
I think it was this morning you mentioned the transactionality.
Ah, yes.
I'm trying to think like how we could improve that.
Oh, into a single exchange, you mean? No, so what I mentioned before, the transactionality is a way of saying that we want to make sure that if you have a sum of transactions, a sum of transfers, and each one of them gets executed independently in a different resource manager, then we want to make sure that they all execute it, because then we can conclude that the sum of the transfer has been, the complete sum of the transfer has been executed. Okay. So here you could say, well, that's a good point here, because here we are assuming we're given something that we call a transfer, okay? Let's assume gamma is, you know, a sequence of position, and every formula denotes a resource, okay? Remember, a resource itself was a coproduct, so it's like, you know, a mapping from, some resource types to something else, okay? Then, what does this say? It says that if, let's assume, you know, this is a transfer, then we apply a function to it, a linear function that says that take that resource in the position 16, the B, and move it into position 17, and take the position, you know, take the A that was in 17 and move it into 16. Okay? What happened to the sum? It's the same. So if it was 0, it's still 0. Okay, it looks good. If we assume that the resources that each one of them, each formula is denoting a resource now, we take the sum of them, let's assume that's 0, we get, we preserve that property, right? And that's a linear map. So basically it's a map from that, it's an automorphism. So the init rule is actually the one that says then, okay, this is interesting because, you know, what's the assumption? So it has an empty assumption. What corresponds to an empty assumption here? No resources, there's no, the indexes we have is the empty set, and the only vector that lives in there is the 0 vector. So the sum of 0 is 0. So that's still valid. But then it says, from this one, we should be able to construct something that is a real resource vector, because it has 2 positions now. But what does it have in those positions? It has for any resource. Now the A could be representing a resource. Remember that? It says for any resource, you put in one position the resource, and what do you put in the other position? Yes, so what does it mean? What do we arrive here? It suggests interpreting the bottom, the negation as, the logical negation as minus, so additive inverse, okay. If we do that, what's the sum? 0, excellent. So let's look at the cut. So let's assume gamma A denotes a resource vector. Yeah?
Just to be clear with the interpretation of the exchange.
Yes.
Any transfer would have to be done in the resources or in basic locations.
So you could say like this, the exchange in the logical rule here, it means that that's limited, that's how it's written here, to one that's moving in adjacent positions. So you could say like, that corresponds to having a particular function. It's a transposition function. And the transposition function has the property to take something that is, 0 balance and returns something that's zero balance. Also happens to be linear, okay? Now you could say, what about other exchanges? Well, we know from logic, actually, we can pose any kind of sequence by applying this sufficiently many times, you know. So we just, yeah. So that's the reason it's the only rule we have, because the other ones can be composed. And in this fashion also, we compose the corresponding functions, you know, the exchange function that does the exchanges of resources. Now let's look at the gamma. And I'm out of time, but let's look at the gamma here, and the delta in the cut rule. Cut rule again, if you look at this one, just you'll really see right away. So if you interpret now the or, the comma now, as, well, plus, right? I mean, so it says that if you have a zero balance vector on, you know, on the left here, and a zero balance vector on the right, we get another vector consisting of gamma and delta, and the only thing we remove is both a and minus a. So if the sum was 0 before, it's 0 again. This looks pretty good, doesn't it? Let's look at the multiplicative rules. What do they say? So how do we interpret the tensor? What would be, you know, remember, you know, the a and the b will be interpreted as resources, not transfers, because gamma together with a is a transfer, that zero balance thing. Now a single a is just a resource, okay? A zero b is a resource. What can we interpret this as? Yeah? Parallel, sorry? Parallel execution, yes, but if we interpret this parallel execution, I mean, in terms of resources. Now imagine now A is a resource and B is a resource. What kind of operation can we apply? The most parallel one is addition, right? I mean, you just, you know, you add those two together. A and B. So remember, A and B, resources, it's a vector space, we have addition. Okay, so we'll just add it. Tensor unit, okay. It's basically, it's got to be 0 again. Here's the one actually playing the role of being produced. So it doesn't really make any thing. And the par, how is that interpreted? Now it gets scary. So remember, actually, we have a resource A as we had here, and a resource B as we had there. We assume that gamma were ownership states, such that, you know, if you add the A to it, we get, you know, zero balance, and we get zero balance here, and then you can check the arithmetic here. It's zero balance down there, okay? If we interpret the tensor as resource plus, so in the vector space of resources. What's the natural interpretation here? So we have a gamma and an A and a B, and the sum of resources is 0, and we'd like to maintain it. We interpret the par as, say it again? Sum again. So par is interpreted as plus, and tensor is interpreted as plus. So somewhere we're sort of like losing distinctions, but it seems like we have a model still that works. Yes?
You need to interpret it as the 0 vector?
Yes, that would be the only one you could, make use of. Yes, 0 vector. Because, you have a 0 vector, and actually interpretation of 1 then is just a denotation for the 0 vector. Just the only one that is 0 balance, okay? So the one you could say, it's now in a position, okay? So it's a bit different thing. Is like, you're going from having no prerequisite, which means like it's the empty set of, so it's the coproduct over the empty set of vertices. There's no position. So there's only like the 0 of that vector space, okay? And now we're going to a vector space that has an index, okay? Namely, it has one index, 1. And we're saying we need now a resource in that position. What resource we use is the 0 resource. Okay, so these two things are different, right? So one of them is the vector is the 0 in the coproduct, and the other one is the 0 in the the one here is the interpreted as the 0 in as the 0 resource. subtle, but think about it. It'll just, once you have this model in mind, it just points out, And then the par thing is basically saying that if this is a zero balance, transfer, then by just adding, A and B, A is a resource and B, and then we again have that, And the bottom actually means that in this case we have to interpret it as 0. Okay. Okay, so and then it gets difficult. Okay, so that's the challenge. Okay, how do whether you can do these things? Okay, but I hope actually for the multiplicative rules, this gives you an idea of actually how you can read these as operations in this kind of vector space interpretation we had, right? Where conjunction and disjunction are interpreted by the same operation, by plus. So how come that's possible? So intuitively, I would say it's because it depends on whether you're operating on negative values or on positive values. So the or makes things more wrong if things go wrong, right? So it's the plus of something negative. Well, it makes it more wrong, right? So if you take two negative things and you add them together, they become even more negative. While if you plus two positive things, so something is true, then it becomes more true. So then the plus corresponds to a, you have more of the resources. So it's more true. So conjunction of two things, you have two proofs of it, so it's more true. And the disjunction, a proof of not being an element of it, you have two proofs that if that to be true, then you have two proofs that it's wrong. Okay. So and that's the reason you could say, oh, okay, might work out. But it would be interesting to pursue, I think, this a little bit more, and see whether actually there is a useful interpretation. Useful in the sense that we get some insight about as a meta language as a language for describing transformations on these zero balance vectors, okay, from linear logic, and the other way around. Maybe there's an interesting logic by adding the k times, for example, I mentioned before, that is sound and can be interpreted here, but which is not part of logic, of linear logic. So I'm just. So additive rules, okay, so this is a wrap up, okay? And I'm late again, so it's terrible. So contract, so this is about smart digital contracts. And I'd like to argue is like it's about digital contracts, and then it's about smart management of those digital contracts, but keep them separate. So we've modeled contracts as a set of event sequences, happy paths. They're a protocol, they don't get executed, or they don't execute anything, they're not a program. Contract specification is something that notes such a thing, and CSL is a language that contains contract specifications. And it's compositional because we have seen very simple, you could say, semantics. So it's not very high. These domains we used are not like high dimensional domains, which would indicate there's a lot of dependencies on contexts in order to make them fit together. Okay. Contract manager is actually now it's a program. Think of it as a service that says that, it's implemented as a generic smart contract, so it's running on blockchain system. It might also be running on your regular system that's not a blockchain system. It's a program that gets handed a contract specification and then manages it for you. But it could do different things for you. We've seen standard monitoring, so a standard implementation of operational semantics, but it could also do escrow management. It's two different programs, okay, for the same contracts. And then we've seen a model of resources that's a finite map from arbitrary resource types, so user-definable currencies, and making sure that a resource manager preserves by having it is one that only actually accepts and operates on transfers. And in this fashion, gives a guarantee that no resource is lost or duplicated. And we have separately from the contract manager, we have a resource manager. That's the one that validates resources, so it's not conflated into the same system. So we can have contract managers that talk to different resource managers and can make sure that this contract that involves these 5 resource managers can work for the clients that use it, and another contract manager and contract that doesn't need those 5 but only these 3 will actually work separately from that. And as I mentioned, the resource manager is system manager's ownership and admits only resource transfers, and the resource transfers are a calculus and algebra that guarantee that resources do not get duplicated by resource managers. And that's as far as we've gotten. So if you're interested in any of these things, so there's actually more. So it's a separation of concerns, contract and contract manager, and separation of resource managers and contract managers, as I mentioned before, because then we can vary each one of them independently. In particular, we can analyze contracts without having them embedded or expressed as programs in a super expressive programming language, okay? So I hope you enjoyed a little bit getting this perspective on digital contracts without, and I have to say that without, and hopefully it gives you an idea that it's not about building chains of, that's one way of implementing these things, of chains of individual transactions that there's a global consensus on amongst lots and lots of different nodes who are actually a replicated state machine. There's lots of designs for doing this one that could involve blockchain systems as decentralized resource managers, or actually just involve regular systems that run on a server, and the server contains basically, all the things that you've produced in your company, and you are the one who is managing ownership of those resources, okay? So there's hopefully a semantic space now that shows what's possible in the domain of smart contract management, including for decentralized systems. And here you've got to think about decentralized resource management systems. That's it. Thank you very much for lasting this long. And I've gone over time again. I'm sorry. I'm totally sorry. Thank you.